Okay, guys, I think we're going to get started here. Just started on this. Okay, welcome everybody. Today we're going to continue on with the parallel library MPI, and this is part 2. So we're going to continue on what we started last week, or on Tuesday. So I introduced MPI as this library for sending message passing library on Tuesday, basically saying it's a library that allows us to do distributed memory computing. It's kind of the main dominant one in that to do that form of computing. It's a little different than OpenMP in that it's not pragma or language specific. It's actually a library, and actually you're handling the message passing yourself. It's sort of a communication library with some synchronization stuff. So we went through the basics, MPI init, some basic features of what you have to do, some sample codes of how that works, and then we got into the utilities of how to launch an MPI job using MPI run. And then we also started talking about how to actually write an MPI code with send and receives. And we ended up breaking MPI or sucking our code and ended up with a deadlock. So for those of you who don't remember, what happens is we were actually trying to create a periodic boundary condition case. We were sending a message from left to right. And that worked fine. But as soon as we tried to put our boundary conditions in from 2 to 0, we ran into a problem because when we use these sends and receives in the code, the send won't move past until the receive is received. So if you have a series of sends all in a row, and every, say, 4 threads here or 3 threads, and they're all waiting on send, nobody can receive. So you're stuck in a deadlock condition. So you have to avoid this type of problem. So the question is, okay, if we don't want to, using the syntax we've learned already, how do we algorithmically change this? Does anybody have any ideas how we would get around this in the code? How do we get it to the point where we want to make at least one of the process has to be able to get to receive, so it can finish the send and then complete that loop? Any ideas? Well, one way is, so this is just describing the sending and receiving, how we actually have to follow back. So they all have to be paired here. Open the buffers. I'm going to skip that for a minute. Without using new MPI routines, how do we fix this? So one way to do this is just do evens and odds, right? If we only send, say we split the communication up, instead of just all send and all receive, which was nice clean, what we can do is we'll just say if mod 2, i.e. if you're even, you send, and then all the odds are going to receive, right? And what that'll do is that'll put breaks here and here and any other interval and allow us to, all the odd ones will send, they'll finish, the receive will receive on all the evens, and then it'll keep going. So that's a way to avoid the deadlock. So does that make sense? Does people see the difference between that one and what we had before? So let's just see what that looks like in the code. So it's basically the same code. Before we only had one send and receive, right? We had this one send and receive, and all the processes were doing it. In this case, if you're even, you're going to send, and then else, basically if you're not even, right, you're going to be odd, then you'll have the receive first. So we've basically just taken the code and just switched the arguments, who comes first, right? Now it's not the cleanest thing, but it'll work, right? Because now we're staggering the communication. Now this will work, and there's nothing wrong with it, but it's not the nicest thing in the world. We can run it. I won't bother with the code because I'm trying to get through some more details today. But in the examples, it's called fourth message. And you'll see this, unlike third message, which just sits there as it hangs, fourth message here, the only change is we've switched these messages around. It completes fine. And now we have our periodic condition, right? Where 0, sent 0, and got 16. Then in 1, it got 0, which makes sense. And then 4 sent 16, got 9. So it actually sent 16 and goes back. So this shows you we've actually completed our periodic vector. There's nothing wrong with that. It works. And in the big scheme of things, it's fine. But it's a little ugly. So let's see if there's a better way to do that. And they've obviously thought of this way to do it. And so there's actually a nice command inside MPI. And this is one that most people tend to use because it kind of solves these problems together. Because instead of before, where I actually had to have a send and receive, they said, well, let's solve this problem for the user by creating one function called a send receive. This one function does both of those things. And what it does, because it's one function, in the library itself, it can handle the deadlock condition. Because you don't have to wait for the code, it's actually doing it within the library itself. And then it avoids, and it does it in a smart way to avoid those type of conditions. So here, it's basically just like putting two sends and receives together. The green is the send part of the message, and the purple, except for the last two, are the receive part of the message. So you still have your pointer, receive pointer, count, MPI type, source tag, and the last two are the communicator, MPI status. So it's easily enough, I could easily just take these two commands and get rid of this part, and merge them together, and now I have a send receive. Now this makes it more easy because you said we always talk about pairwise communication. Wherever I have a send, I have a receive. Now in the language, I have them to go together. And if you really want to be tricky, the send receives don't actually have to work on the same send receive. There are ways. You're like, why is there two different tags? Well, because if you really wanted to be, you're saying if it's part of the same message, why wouldn't they have the same tag? Isn't that redundant? Well, it is possible to actually have a send receive send a different message and receive a different message. Don't do that, but it is structurally possible to do that if there was a reason to. Okay, so that's the question here is why is there two sets of tags? Because technically you can, it's just two messages jammed together. They don't actually have to send receive the same. So say you had some sort of staggered messaging that you're sending, you could still use send receive and do that. Okay. Yeah, so this replaces in the code. It looks a little cleaner than this one. Now we can just use one function call. It's messy, don't get me wrong. These are big ugly messages and you're not going to function calls, and they're very C or Fortran-like, and they've got this big long argument list. However, once you set them up right, you're good to go. And now you know they're paired structurally they're paired. You don't have to worry about breaking the code to do that. So you run it, and in fifth message here, you get the same solution that you would here, right? And you should. And if you did this a billion times, you would notice this one would probably a little bit better in performance. Because the other one, you were going to stagger messages, so you had to go through twice. This one, under the hood in the MPI library, it knows they're tagged, so it can do some performance things. So it's a little bit better. And the biggest part, though, is from a programmer's point of view, I have one source to send my messages. So usually if I have less code, less places to make a mistake. Okay? And the other thing I want to go back here is this buffering. You might have noticed that the messages we were using, actually, where did I put it here? Here, there's different types of sends. Safe send, send, I sends, and IB sends. This all has to do with this idea of buffers. Now as we talked about, in MPI, you actually have to create a receive pointer and a buffer. Basically, you're handling the memory, so you create a buffer. But under the hood, in the message passing library, it's also creating a buffer, right? You're giving it some certain memory and putting on, but it's also controlling how things go out. And so the different types of send and receives, as we talked about, MPI has like 200 calls, actually refer to how the memories go along. So we tend to like to use the safe send, and it's blocking, but no buffering. So the blocking is it'll wait. We've talked about it. It'll wait until it's received a successful signal to move on. That's fine. We want that. But it has no buffering. And the good thing is the no buffering means we don't have to worry about the integrity or flushing the memory buffer or making sure that the data is up to date. Because if there's no buffer, right, yes, it might save her a little bit of performance, but it's a safe send. So it's the one you can trust. So that's why you'll notice in the message calls I was using the S send. As I said, it's always better to start with these type of sends, the blocking safe send versions. And then if you really want to get into profiling and performance, you can unroll some of the performance and say, maybe if I tried buffer sends, now that I know the code works, I might be able to get some performance benefit. So it's kind of like taking the training wheels off. So it's a little undefined though too, because if I'm on Ethernet, it maybe get buffered in system memory. If I'm on InfiniBand, it might be buffered on the InfiniBand's HCA card. You don't know. The standard doesn't say that, and so it's why it's a little bit more undefined. The I-sends and IB-sends, these have to do with unblocking. We're going to talk about this at the end of today's class. A buffer is just a storage place. So a buffer is just an array. So a buffer is, the terminology is why it's used. It's literally, okay, I've got a piece of data and I know I'm going to be sending it somewhere. So I have to have a place to put that, a temporary place. Call it a cache, whatever you want to call it. In network parlance, it's just called a buffer, a reservoir, you know, if you're talking whatever you want. And so whenever we move stuff around in a computer, especially in memory, sometimes things are buffered. What that allows you to do is it allows you to get ahead of yourself a bit. And so in the system, when I you know, go to a web page, right, and it's going somewhere, well, it's creating a temporary buffer in the network to pull that information up. Otherwise, you could always have to send and receive, and I'd have to make sure the sender and the endpoint have exactly the same amount of memory available. The buffers smooth that out, right? So it's a communications thing. As I said, from a programmer point of view, it's much better if you just ignore it and think that this goes to here directly, and you never have to worry about this theoretical buffer. You don't want to have to worry about it. Yes, it may help you with performance, and they're there for a reason, because they definitely do help performance, especially a lot of small messages. You can imagine if you're sending a bunch of little tiny messages, if you had no buffers, there'd be a huge latency overhead, right? Anyway, that's communication stuff. I don't want to get into all the details of that. It's just with it, because MPI is fundamentally a communication library, there are two flavors. So it's just a warning. Don't worry about it too much, but just you kind of have to know at least the bare minimum to know that there is buffered types and non-buffered types. If it really comes down to performance and you need to get into that, you can get into that at the time. It doesn't change how you code because you don't control it. It's just FYI. Yeah, so this is the worst kind of dangers because usually this is fine, but every now and again, if that buffer fills up, you'll get an overflow and you wouldn't know about it. So you can run into, you switch interconnects, you go to a faster system, you go to a bigger problem size. Maybe your 10 by 10 code worked fine, but now that array is 100 and you've overfilled the buffer, right? Your bucket's full, so then you don't know about that and you get funny performance things. So, as I said, avoid it for the first little while. Once you really get into your code and you want to talk about performance, that's when there's optimizations that can be done. The good thing is it doesn't change how you stylistically change your algorithm or how you program. You would just change the function call. And that's kind of the model of how it's designed. So that was just, I just wanted to point out okay. So we got to send and receive. We talked about buffers. I briefly mentioned blocking versus non-blocking. I'm going to talk about the end. All these calls are blocking. As I said, they wait for them, and that's in the send and receive is blocking. I.e., it's going to go to that function, and it's not going to go anywhere until those messages on both ends are completed, sent and received. So that's good stylistically. You can imagine that could be bad for performance, though, because if I have to wait, anytime I'm waiting for a message, that's work, that's inefficiency, right? That's lost time. If I'm only doing that a small percentage of time, that's fine. But if I've got a really big code or I have an asynchronous algorithm, I don't have to wait all the time. So there's another version of MPI or MPI calls that are non-blocking. And they're set and forget. You just go, send the send, and it just starts, as soon as it sends it, it just goes right on. And we'll talk about that at the end of today, okay? So there's two fundamental differences, but primarily what we're doing with today is our blocking calls because, once again, that's where you should start from. But there's performance reasons to do non-blocking later. Okay, so the other type of operations are so we talked about in MPI, there was three main groups of function calls. There was pairwise communication, send, receives, the ones that are actually doing the work. There was ones that do memory copying for handling memory operations. Those are sort of under the hood. You don't see those because they deal with all the buffers and stuff, and you normally don't have to get them. The other type is called collective operations. These are like a little higher level. Instead of you actually manipulating one individual message sending from point A to point B, these allow you to do collective operations. These allow you to do things like sums or reductions or a global OR. And so instead of me sending one message and actually having to collect all the data from every one of you and then sum it together, these collective operations allow you to do that in one operation. they also allow me to say a barrier is sort of a collective operation. Everybody stop, right? And I can do that in one function call instead of having to send to each individual process. So under the hood, they're just a series of send and receives. The MPI is trying to make some of these more common data distribution or message passing, like messages like I read in a piece of data and I want to send it to everybody. Or I want to do a reduction or do a simple operation that works collectively. I can save a lot of this type of stuff. And so they have built-in intrinsics. The good thing about these intrinsics too is a lot of these are fairly performance. It's like using a BLAS call or an MKL or a local low-level square root call. A lot of the networks or communication libraries have these fairly well optimized, so they can do them fairly efficiently. So you're going to be way more efficient than what you would actually be able to program. So you want to use these as much as you can, and this saves a lot of overhead in code calculation. So as an example, you want to calculate, the min, mean, and max standard type stew. You're doing an L2 norm of something in your calculations. So how can we do that? And a collective operation is easily how to do this. So starting with the basic MPI code, like we've talked about, we include the MPI header file, set up some local variables. We always have our init. We figure out who our size and rank are, how many of us there are, and who I am. That's the rank. Where do I fit? I could write this calculation where I generate some data. Got some random generator here, just a bunch of data. Now I'm going to find the min, mean, and max of it. So I find min, mean, and max just by doing a typical sort of calculation here. There's nothing fancy here. Just looping over a series of data and storing some temporary data values, finding the mean, dividing it. Now, if I was going to do this with my own MPI, I want to send this to everybody else. Well, then I have to do, I'm not going to go through all the details here, but I actually have to do quite a bit of work because I've got to send from this 0th guy, and everybody's got to receive it, and then I've got to collect it. And you can imagine this is going to run into problems because, well, it's not going to run. It's going to work. It's just I'm actually have to code a lot because now I've got to make sure I collect everybody's pieces of data, send it back out, and it's a lot of bookkeeping. That's quite inefficient because that first, guy's sending messages and he's sending to each one of these guys and the totals. So it requires P to the 1 messages. And if everybody needs to get the answer, I have to flip that upside down and send it back out. So I'm sending a lot of messages that I needed to do if I'm going to control this myself. But there should be, this is such an average operation, you think they'd have a better way. So the better would be do a rolling sum, right? Whereas, if I have 4, 1 and 2 are added together, 3 and 4 added together, then they add 1. So I get this tree-based algorithm. Now I could do that, but that requires me to program a tree, which is a little more complicated. So ideally somebody else would have done that, and usually they have. So that's a requirement of any of the modern. This has been in since MPI 1. So there's a whole series of these ones, MPI calls that have _all and then an operation. _all means everybody in the communicator is involved. So unlike the send and receive, which had a specific processor and a receiver, so they're really only between 2, anything with the all has to involve everybody in that communicator. Now remember last time we introduced the idea of a communicator. MPI COM world means everybody who started, but I also can make my own segregated communicator to work on a subset. So I can do that too. But just in the terminology, anything with an all means everybody who is going to be part of that communicator is going to work on this. So this is an all reduce operator. So same idea, you give a send pointer, so it's working from me at, say, wherever. They all must have that send pointer. They're all going to have a receive pointer. There's a length of it, and then I'm going to, MPI types, very similar. I'm going to introduce this new operator called Mpi Op. So that's one you haven't seen before. And what that is that's telling me, what do I want to do with this data? If I send an array in my send pointer and my receive pointer, what do I want to do with it? So if I want to do a sum or a min, a max, or a product, anything that can be done in a collective operation, right? Now, one caveat I will notice, be careful of this is, mathematically you could run into problems with this operator. It doesn't always, I might get different answers each time. That's kind of, I'm setting that, you're like, why would I ever want to use a function that might get different answers? Well, this comes to community of error, right? We know if I add A, B, I know mathematically I can add A plus B plus C, and that's the same, that's equal to C plus B plus A, and it shouldn't matter which order I do those, right? That's perfectly true for whole numbers. We know with floating points, that's not true. Because if this one is 10 to the negative 17, and this one is 10 to the 7, and this one is 10 to the 7, if I change around that order, I'm going to get a different answer, right? Because the round off is different. So the thing with MPI is MPI says this is true, fine, but it doesn't check like this. So you have to be careful using an all reduce operator, because when you run it, it might go 1, 2, 3, and the next time be 3, 2, 1, and then 2, 3, 1. Now, ideally, you should be doing some control of your own, round off in your own code. But just this happens. Some people run MPI and they're like, I get a different answer. And I look in their norm and it's just off by a little bit, right? But they might get a different answer. But if you're doing, say, optimization and your gradient's off negative 10 to the negative 7 in one direction and plus 10 to the negative 7, well, you get a completely different problem. So it's just be aware. It's perfectly fine to use, but it's not guaranteeing a floating point operation, because unlike in a serial code where it's always 1, 2, 3, 4, you could easily have processor 2, 1, 3, 3, 1, 2 go on. It's a solvable problem, but it is one of the things that commonly happens with numerical codes, especially with large floating point. Now, if that's MPI int or character, you don't have to worry about it. It's deterministic. It's going to be fine. But if you have floats or doubles, you can easily run into that. Okay? But it's very, very powerful because it replaces doing inefficient things like this. Which, again, with all this extra code, send, receive, everybody's sending it in a different way. And we can replace that with 3 columns. Much easier, much more readable, and it's done in a more efficient way. So it's probably second most used operation in scientific codes is all reduces. Because invariably across multiple things, you're doing norms, you're doing an error calculation, even just passing an error code back and forth. You can do a reduction with an OR, right? And then you can actually see, did everybody successfully complete? Because they're run independently, just because you get an error on one part of the code on one processor doesn't check it globally. So a lot of times people will you'll see after the checks, they'll actually do an all reduce on their error codes to make sure we're all at the same spot, so we don't get one running ahead if there's a problem. Does that make sense? So once again, it's fairly straightforward to use. It's just all you're really going to do is just change the operator in each one of these. Okay. Okay. So collective operations, as I said, we've already talked about this, is all processes that are used in the communicator must participate. So the good part is they all wait for each other. The bad part is they all have to be at the same time. So it turns into a synchronization point. So say you had a load imbalance. With the send and receives, that would be fine as long as those two are in check. They would go on. This one requires all of the processors. So that means that if you've got one doing 100 integers and one doing 1,000 integers, you're going to have a gap waiting. And so one of the processors could be sitting there spinning around waiting for its time. So this is why if you use these all reduces, they're kind of like intrinsically with a barrier built into them. That's fine. It's just you got to be aware of them, and you could easily, this commonly comes up in profiling, you'll see big gaps in performance or scaling because one guy, whoever is doing the longest amount of work is going to hold up everybody else. Because it will not pass this line until everybody, all ranks, go past it. So if you really so I just mentioned that as I said, it's a control structure, but it also means that if you want to create a communicator and you only need to do a sum on a subset, not everybody, create a sub-communicator that's only on that subset, because you don't want, if you don't have to use everybody, don't use everybody. So people get the idea of doing a collective operation and a standard communicator? Good enough anyway. So let's talk a little bit here about a specific MPI example. Okay, this is all well and good. We don't care about communication theory. Let's actually apply this to like a real world problem. How does this fit, or how would I apply this to my workload that I want to do? So in MPI real problems, you always have various type of stencil schemes, time marching methods that work. Domain decomposition is how we're going to split up the problem, because you need to divide and conquer. Unlike the OpenMP, where you can just do a loop based, where I just look at the for loop and I need to break it in tasks. Fundamentally, with distributed memory codes, I actually have to target out big enough chunks that I can do them completely independently and only communicate where I need to. So the most common way to do that is to just break up your physical domain. It's not the only way, but it's very common, and you'll see some examples. We're going to talk about load balancing. I've already hinted on the point. That means is that ideally, you'd have the exact same amount of work for every processor, right? If I'm counting the numbers from 1 to 1,000 and I have 10 processors, if I give everybody 100, if they're all the same speed processor, right, then I have the same amount of work for everybody. There's always going to be a little variability, but if I have, say, a 5 or 10% imbalance, that adds up quickly because it's not just 10% imbalance on one CPU, that's a gap on all of the CPUs. You can imagine as you start to scale, you're going to start wasting quite a bit of cycles. So you try to strive for perfect load balancing. You can't always, but you do your best, right? Other things we have to run into, we've already started how to solve that. We always commonly end up with global norms that we have to get, and also about how do we handle boundary conditions. So these are typical types of problems, and we're going to talk about how you sort of get around them, or how you'd think about your problem to set up with an MPI code. And as I mentioned multiple times, one of the trickiest things about MPI is not the MPI itself. MPI is actually pretty straightforward. Yeah, it's messy, it's got some function calls. Most of the time, it's finding the function, putting it in. The trickiest part is thinking how I need to break up my code, especially if it's an existing code where it has an algorithm with a lot of data dependencies. Now, if it's an explicit algorithm, like a typical time marching code, it's not too bad, because if we just looked at our, say we just have our number line here, and I'm time marching across these various, it's finite difference scheme, 1, 2, 3, 4, 5, 6, 7, 8. We look at a standard finite difference, second order or first order method. I'm only dependent on this guy here, only depends on this and this. What this guy's doing over here for that time step has no effect on that one. Yes, they have to be in step for my time step, right? But the data dependency is quite straightforward. So I only need information from my next nearest neighbors. That's good. Now, if I have some sort of large implicit method where I've got a big matrix I'm solving, it gets a lot more complicated, because now, like any matrix maths, I've got rows and columns dependencies, and that becomes a lot more tricky. So we're going to focus on just the explicit schemes right away, because they lend more easily to think about in parallel. But that's not to say you can't. You can definitely do implicit methods, and there's a lot of good reasons to do that in parallel. It's just now you have to do a lot more communication typically to solve your problem. So there's nothing new you guys haven't seen about this. Your previous homework that you're going to do in the OpenMP, bury the lead here that, yeah, you're going to basically do the same thing for the homework for the MPI course. You're going to take the same wave equation, but you're just going to, instead of using OpenMP on it, we're going to break it up with MPI. Big surprise. Just basically, you should get the exact same thing, it's just now you're going to be able to distribute. Difference is how you code it is going to be very differently. You're not going to break up those loops. You're going to have to physically break up the problem, right? So if we look at a diffusion equation or a wave equation, we can break up this finite difference in the scheme. We get a time step across each one. The data dependency is really only on our next nearest neighbors. Now, if we went to a higher order scheme, we'd have to increase our stencil size. Then we'd have to send more information. But in 1D, we can get away with second order by just using our left and right. And not surprisingly, that looks very similar to the work that we talked about, sending our data to the left and sending our data to the right. Because in 1D, we only have a single piece of information I have to send back and forth. If this was 2D, it's really just the same thing. I have a grid. Let's say it's, I'll make it 4. If I wanted to split this up, I could easily just split this up. And now I have a whole column of data that I have to send back and forth. And in 3D, it becomes a whole slab, right? It's the same idea, in a structured grid sense. It's just I have more data to send with. So it really doesn't, it's more tricky, more bookkeeping, just like anything in 2D and 3D, instead of I've got to go in both directions, but it's the same idea. So we're going to deal with 1D because it works easier and it's much easier to debug and quicker to solve. Okay, so we commonly, you guys have probably come across this, we introduced this idea of buffers, or effectively guard cells, or some people call them halo cells or ghost cells. It depends on which discipline you're in. And this is an idea of if I want to break up this problem in parallel, right? I have this piece of this typical grid that I have. This is my grid. Instead of, we'll call it a real grid, and we'll call it cell values here. Well, if I wanted to split this in half, on one processor, it's simple enough. I probably didn't count this out right. Yeah, I've got too many here. I get 3 on one, and I get 3 on the other, right? Now I'm load balanced, right? It's pretty straightforward. I split the problem. I'm done. So the part where I need to do communication is between here and here, right? On 2 processors. Well, what I have to do is I have to be able to get this information on here and on vice versa. So the easiest way I can do that, and you've already seen this if you've done that. I'm going to erase this one just to make it simpler. You'll look in the wave equation code that you have out already for like boundary conditions. We commonly add an extra cell at the end here if I'm applying the boundary condition, right? We go 0 to n, but then we add these 2 other cells for the boundary conditions, because that way when we do our finite difference stencil, I can use that boundary condition as part of my stencil, and it applies to the boundary. Great. Well, we're going to use exactly the same approach in parallel. So now I'm going to, well, actually these are not this small, they're actually this big. I'm going to add an extra cell on the end of each of our domain. So instead of, if I divide it, there's 10 cells, and I divide it in 2, it's 5 and 5, but really it's going to be 7 and 7. Because I'm going to have an empty cell on the end of each of these. And what that allows me to do is add this data to here and this data into here. I need a place to hold it, right? And then when I apply my differencing scheme, I just start, instead of at 1, I start at 0. So you can basically treat the problem as a series of discrete individual problems with just boundary, and these MPI interfaces are effectively a boundary condition. And that way you can see conceptually when you loop in your code, it really doesn't matter. You might load the information in a boundary condition different, and how you load these one is just by MPI calls. So that's conceptually, this involves domain decomposition, right? This introduction of these halo cells, or ghost cells, because they're not really part of the physical domain. And it solves your communication buffer problem, because now you've already got the memory to copy that data into. That makes sense? It's a pretty straightforward idea, but it solves a lot of problems, and it actually makes procedural programming way easier, because now you're really not doing anything different. The only thing different is you have an MPI call to fill this information in the outside boundary condition, right? So the domain decomposition gets a little more complicated. We're not going to get into this, but as you get to more complicated problems, you got a cube sphere type thing. You have to wrap boundaries again. You end up with degenerate corners because things are funny. That's with structured grids in the top corner. If you're doing unstructured grids, triangles, you get funny shapes. The good thing is there's lots of nice decomposition algorithms that'll do this for you. Parmetis or Scotch or these are various ones that are written to basically do space filling curves, and they figure out where the best spatial, split is for you. A little more complicated to work with. If you're interested in that, this is a well-trodden problem that works out quite well, and there's reasons to do it for space or do it in time. But the main reason is you have to break up the problem. How you break up the problem is very much commonly it'll be based just on physical domain, because that's an easy thing conceptually to think about. But there may be a reason to do it in temporal or spectral or other reasons as well too from math. But we're going to do the very simple methods where we're just going to split it up in a physical terminology. But when you're talking parallel, especially in distributed memory parallel, you have to break up the problem. You only have your piece of the problem on your computer. You never have the global problem. If you ever needed the global problem, it's not distributed memory, because at one point you're going to need as much memory as you have in n processors in one machine. So if that's in your algorithm, it's not going to scale. Because if you're doing this on some large system with 10,000 cores, if you have a gig on each core, you're suddenly at 10 terabytes of memory. And there's not a machine out there that's going to be able to allow you to pull that back into one system. So it's another fairly straightforward physical interpretation, but it's important to be aware of and how it affects. So this is kind of the the flavor of how you would write this code. So you do so you can take your serial code, right? You do the computation. Now, normally you'd apply the boundary conditions, but in this case, you do your guard cell exchange. You would actually copy, you make a send receive, send some information to the left, send some information to the right into that buffer. Then you can apply different methods here. So if the rightmost, you send it to left, you send it to right. You can use an even odd trick, but I wouldn't do this. I would actually just use the send receive. It's a much easier way to do it. And then if you're using like a fixed temperature beast, like this is specific to a diffusion problem, you just uphold the boundary conditions at the outsides. And the last zones are fixed. Basically, they're just saying applying, all that really should say is just apply the boundary conditions. So really, it doesn't change the flow of how you would normally calculate this in a serial way. The difference is that you're just gonna, instead of having n total points, you're only gonna work on your local points. So before you do your calculation, you're gonna have a little bit of math at the top, just like we did way back in our messages, sending who goes left, who's my right, and how many pieces of data do I have to work on. The rest of it, you don't care about, because your data dependency is only on your next nearest neighbor, right? In this type of, so that's why these explicit time marching schemes can scale really well, is because they're only dependent on one piece of data on the next nearest. Okay? So that will, this is all the really codes you need to use for this, for your assignment. As I said, I guess we got away with 6 Mpi codes. That's not too bad. You know, the trick here is not, once again, the init.com, well, I guess you have to call that twice. Does that count as an extra one? But anyway, 6 independent ones. And then you don't need send and receive if you use send and receive, so that's redundant. So you really could do this whole assignment with 4 Mpi code, Mpi functions calls. So that's not too bad. But the trick is actually going through the code and figuring and thinking in parallel to how you're going to split this up. And those are the communicators. So this information here is really, don't worry about it right now. It's there just when you sit down and do the homework, go back to the slides and step through these, and it'll make more sense to sort of set that procedure of when you're going to program, how you're going to go through it. Okay? So does that sort of conceptually make sense for what you'd want to do for in a real sort of world example, or at least a toy real world example? All the codes that I used in these slides, the first 1, 2, 3, 4, 5 messages with all the different types of MPI are on the system as well. So you can clone them out of a Git repository on Signet. There's a make file there. It's very useful if you just want to play around with the syntax and cut and paste. Be my guest. That's what I do. Okay. So the other thing I lead a little bit, and I'm just going to spend the last little bit talking here at the end, is the difference between blocking and non-blocking communication. So all the current communication we talked about was blocking communication. The whole point of the whole reason we had a deadlock was because the send wouldn't go until it was sure it had to receive, and that's very good from a programming point of view, and from initial setup to make sure that our communications are all paired. The problem is it's pretty wasteful, or it can be wasteful. I shouldn't say it's only wasteful. If you're perfectly load balanced, then you may have no problem with it. However, typically that's not the case. If I'm sending a message and I'm a little bit slower than the guy next to me, I should be able to stop, send that message, go do some other work that's independent, right? And then come back and check a little later that work is actually, that I've actually got the data I need. In order to do that, we need to turn off the blocking and have a non-blocking version, sort of a send and forget, and then a checking mechanism. And those are the two fundamental, and there is. So that's why most MPI communication is either referred to as blocking or non-blocking. So what happens with blocking communication, this is an idea of a profiler, and Intel has a trace analyzer. And blue means that's something your CPU is doing. That's the good work. Red means wasteful. That's empty times. So you want those blue sections, those red sections to be as small as possible. So you can kind of see what's going on here. You get a bunch of work, you send some messages, you do a reduction, you do a bunch of work, you send some messages. But what you can kind of see going on here is on this last CPU here, this work, for whatever reason, maybe it has more work to do, is quite big. That's fine. But what happens though is because we're doing well, actually, let's look at the reduction operator. It's even more of a blocking. because we've got 11 processors going, or 12, I guess, if you count 0, at the same time, these guys can't start this application until it has all of them get to this point. And there's a little stagger, but effectively it's all starting right here. So you can see this guy's done first, but he can't do anything until this guy gets done. And then all the time the operation takes. So when this is the time the operation takes, you're actually wasting a bunch of calculation here. Now with an all reduction, there's not a whole lot you can do about that because it's a reduction operator. But in the send receive, you can see the line here, he's sending to him, he's sending him. See how this one here has to go all the way back up here, you can't quite see it. You can see there's quite a bit of wasted calculation. So this red is overhead. You know, it's wasted time. It's unavoidable to a point, but if I could actually send this message here, or in this case, send here, and go do some work and then wait until this guy is done and I get it over here, I could do another chunk of work inside here if my algorithm allows it. And in order to do that, I need non-blocking messages. So this is commonly here, this is a mechanism for overlapping or interleaving the communications. Do the communication quickly, go do something else, come back and check if you can. This fundamentally avoids deadlocks, right? Because you can't get a deadlock if I can set and forget. But you avoid system memory and you avoid memory copying. The problem is you have more complexity. Now instead of a simple send receive, I'm going to have 4 new MPI calls that I have to check. So all the non-blocking ones have an I in them. They're the I sends, I receive. So it returns immediately. It posts a request to the system and it says, library, it's your problem to figure this out. I'm going to go do something else. But it's not completed. You can't mess with the memory that is sitting in that buffer because it may not have sent it yet. So if you have some temporary buffer, you can't go and overwrite it. If you do, you may send the wrong message. So you kind of have to set that aside and don't touch it until you're sure it's good to go. So that's another thing. You've got to handle a little more memory. You got to handle a few more messages, but you may get some performance. So with these cases, you don't have to worry about it because the sends are automatically going to complete. I don't have to worry about it. So now I can actually just have my pass to left with my periodic boundary conditions. I don't need my null cases or odds and evens. I can just do that. I don't have to worry about it because there's no deadlocks are going to happen. I replace, this was the even odd messaging cases. We talked about this, we'll skip that just to speed up. Instead of doing that, we have the send receive. So this is what we were going to use in our blocking case. Now to replace that with a non-blocking message, we need to do this. So I have to add a few new pieces of information. I still have my message buffer, the size, the type, where it's going, right? In this case, the tag and the column world. But I have this new extra piece of data stuck on the end, and that actually to do with an MPI request. That's a flag that I have to tag on there because I have to go over and look up that guy's information. I need a tracking number, right? I have to be able to, put in that tracking number and say, have you left the building? Is it going to go to my doorstep yet? I don't know. So that's what that send request is. It's effectively your tracking number for that message. And you have to be able to access that tracking number. And that's what these guys are for. These MPI waits. Because you might get to a code, you go ahead and do this stuff, go do some other work here, but now you're still going to get to a point where I still need that data. I can't, put up my next step until I get that piece of information. So that wait, well, I can put it on the send request and the send stat, or return that, and it'll wait until it gets there. There's a wait all. I can wait on a whole group of messages as well. So you can kind of see how if I take this one and this one and this one, all 4 of these, and slam them together, they're just a send receive. So if I just put all these in a row with nothing else, it's exactly the same as a send receive. And that's exactly what's happening under the hood. Under the hood, that's what the send receive is doing. You're just, if you want to manipulate it, you have to break them out into a few pieces yourself. And that involves a little more programming. So just to reiterate, it's the same sort of thing. The only new piece here is this identifier. The rest of it, it's the same idea. So commonly, I recommend people start with the send receive or individual sends and receive blocking ones. Get your patterns worked out. And if you start, when you profile the code, there's some overhead. You can easily go back, put an I there, tag on a request, and if you do this in a modular framework, it's very easy to do, to determine. Don't, as usual, don't program something. If you're only doing one send receive and it's 0.001% of your problem, who cares? It's not going to show up. But if you have an algorithm that's maybe maybe unload balanced, or you have a lot of extra overhead, or there's a lot of work that can be done, it's worth the trouble to spend to split it up. The wait, we've already mentioned, this is a way to check the communicator. Wait all takes an array of communicators, so this is useful. I may have sent 20 messages to my neighbors and all this other stuff, and I get to a point where it says, I can't do anything else, I want to be safe, because I can't work on that data because now I finished my time iteration, I can't go anymore. I need to be able to hear, so I can use a wait all instead of having 20 waits. So commonly you'll see these requests being an array of a request. So that way you can just track and loop through them all. It's a much easier way of bookkeeping instead of having to have a bunch of individual ones. A test, this is not used that much, but you actually can also query. Instead of having the wait, you could say, maybe I could do some more work, but I'm not quite sure. You can actually test and see if you've got it or not. If you do, you might be able to do something else. So it's sort of like halfway between a wait and a barrier. A wait is only going to go if it finishes. It's a blocking communication. But a test, it'll just say, do I have it yet? So maybe you don't know how unload balanced your problem. Typically, you shouldn't have that, but it does have that function as well. So it's a mechanism to allow you to check your tracking number, not just wait at the door. So if we look at our diffusion problem here, or our typical finite differences, before we couldn't, when we were doing our blocking communication, we had to wait till these two neighbors completed their communication. But as we said, this data here, the only guy that relies on this next step of data is this guy, and this guy, right? All the interior cells, if you have 100 cells, only 0, 1, and 99 and 100 actually care about those data. The internal stuff, as long as it has the last step's data, doesn't care about that. So what I could do is I could loop twice. I could send my message, loop over all my interior points, get the new message, and then just update the very last 3, right? And that makes more, and when there's only 4, it doesn't make any sense. But if you have a big cell with 10,000, it makes a lot more sense to break that loop up and loop from 10,000 minus 2, or minus 4, I guess, loop over that, then come back, and you can do all that while the messages are going on. So you do the inner zones while the other ones go back to do that. So it's another option. And actually in most real world, like CFD and those type of codes, this is what's going on. You want to decouple that because waiting for messages is unnecessary. Now in this 1D code, if you did it both ways, you probably won't notice the difference because it's such a simple, you're only sending one piece of data. But as you can imagine in a 3D code where I'm sending a whole slab, I've got 100 by 100 by 100 mesh. So I'm going to have to send 100 by 100 cells, an array of how many vectors each. There's quite a bit of data there. There's going to be some overhead. So you probably want to do this. And it's straightforward to do. Yeah? Sure.
You want to do a cell.
Yeah.
I have to wait sending it off.
What do you mean in terms of so
I do my Mpi sending.
Yeah.
And I do, as you said,
the interiors,
1,000 except for
the last 2, yeah.
One count as the one doesn't count as the extra, right?
No, well, I'm going to have an extra cell on the other side of.
So my question is, in this setting receiving, because I'm sending 0 to like the area,
Yeah.
that doesn't, I can access.
Oh, you can always access the memory. You're fine to do that. That's fine. You can access it. It's just remember you're reading it, so you're going to read the old one. It's all about am I working on new data or old data, right? The only piece that I'm actually caring about, I have the new data from the last time step here. So even though I can't update those cells, I can still read it, right? Because that's fine. I just can't replace it with a new guy. But that's a critical thing is you got to remember, am I working on old data or new data? And so that's why order of operations is very key. You got to send the messages, do it, and then that's exactly what you're working on. Because otherwise you're going to get out of stagger on your time series, right? But it's totally possible to work on the old data. That's perfectly fine. So here's just an example of how this would go about. I'm sending right guard cells information, sending the left guard cells. I've got I-sends and I-receives. Once again, I've had to decouple this. I've got an array of requests of 4 long. So once again, it's a little more MPI, right? Then I do my time step, then I have us wait all. So it's messier than that send receive we had back how many pages ago, which is 1. So I mean, if you're doing your assignment, you don't have to do it this way. I would recommend you stick to the send receive. Because you go ahead, do it, send receive, and then make another copy if you want to play around with this. But there is some performance reasons to do it this way. Okay, so just to let you know, type of thing. There are other collectives. I'll just go through them quickly. They're at the end of the slides, just to sort of fill out. We've already talked about collectives. Most overly used and one that people like to throw out is barriers. Barriers in a collective operation just says wait. People like to throw it in their code all the time because they're paranoid. It's kind of redundant. If you do a wait all, you do a blocking communication, you do an all reduce, the barrier is implicit. It's waiting anyway. Admittedly, I will use it in some places too for debugging. Okay, I don't know what's going on. I'll put a barrier and then figure out, I know it won't go past that. It's fine for that, but once you're done, get rid of them out of your code because they're just unnecessary. They're empty wait statements in your code. There's data ones for doing broadcasts. So a broadcast scatter, these are just for handling data. This is very useful. One guy reads the input file and I want to set up my piece of data, he sends it to everybody. Then you can do scatter where maybe I read in one data file and then I distribute the work. I could do gather by collecting it back up, and then there's reductions. We've already shown that that's a very useful one. But you can also do this for handling data. Scatter, gather, and there's different versions of that. So if you're manipulating data, these become very useful for handling that. Yeah. So these are just the collective operations, the barrier, the broadcast, very simple functions. This is just sort of rounding out the list of, that's the end of it there anyway. So the barrier is really simple. It just takes a communicator, everybody on this communicator stop. The broadcast, just load a buffer, send it to everybody. And the only flag you need is the root. Who am I coming from? So everybody is involved, but who is it sending it? And then everybody else receives it. So usually root is 0, but it may not be. Okay, so that I think finishes that up. Okay, is there any quick questions on that stuff? I'll post the homework. Oops, save and exit. Anyway, okay, I'll post the homework later today, and it shouldn't be too exciting because it's really just the same as the previous homework, but you'll do it with Npi.